Okay, so in this video, we are going to be reading sketch 15 of Math of the Ages. However, I missed the last paragraph of the 14th sketch. So I'm going to start reading the 14th, the last paragraph of sketch 14 into chapter 15. Okay, sorry about that. Okay. Mathematician E.T. Bell once said, Euclid taught me that without assumptions, there is no proof. Therefore, in any argument, examine the assumptions. The prototypical logical system underlying all such axiomatic analysis is the plane geometry of Euclid, a way of organizing ideas that is as relevant today as it was when Euclid first wrote it down some 2,300 years ago. Okay, let's begin sketch 15. In perfect shape, the Platonic solids. Yes. The Greeks were very fond of symmetry. You can see it in their art, in their architecture, and in their mathematics. In plane geometry, a major area of Greek mathematics, the most symmetric polygons are the regular ones, polygons with all sides and angles congruent. A regular triangle is one that is equilateral. A regular quadrilateral is a square. In three-dimensional space, a polyhedron is regular if all of its faces are congruent regular polygons and all of its vertices are similar. For example, a cube is a regular polyhedron. All its faces are squares of the same size and each vertex has four squares adjacent to it. It is a remarkable fact of geometry, proved as the final proposition of Euclid's Elements, that only a few convex regular polyhedra exist. Contrast this with regular polyhedrons, which can have any number of sides. In fact, there are exactly 5 different types as pictured in display 1. There's a tetrahedron with 4 faces, triangles. There's a hexahedron, which is a cube, 6 faces, squares. There's an octahedron, 8 faces, triangles. There's a dodecahedron, 12 faces, pentagons, and the icosahedron, which has 20 faces, triangles. And here they are. We know them well. Page 166. The fact that there are only these 5 regular polyhedra may seem puzzling at first, but it's not hard to see why that must be so. Think of it this way. To form some sort of point or peak, at least 3 polygonal faces must meet at any vertex of the polyhedron. Since the polyhedron is regular, the situation at any vertex is the same as at any other. Therefore, we only have to consider what happens at a typical vertex. Next point. In order to make a peak, the sum of all the face angles at the vertex must be less than 360 degrees. If they add up to exactly 360 degrees, they would make a flat surface. Since all the faces are congruent, the angle sum at a vertex must be divided up equally among them. And the last point. Now let's look at the possible types of regular polygons that might be used as faces of these polyhedra. So triangles. Each angle of an equilateral triangle measures 60 degrees. How many could you have together and still total less than 360 degrees? Well, 3 is equal to 180. 4 is 240 degrees. Or 5, which is 300 degrees. See display 2. That's all. So putting 6 together would give you a flat peak, and more than that would be too large a total. These 3 possible cases give you the tetrahedron, the octahedron, and the icosahedron. It's interesting, I had never realize that before, but I guess it makes sense. So if we look at squares, each angle measures 90 degrees. So 3 of them, totaling 270, could meet at any vertex of a cube, but 4 is too many. And pentagons. Each angle of a regular pentagon measures 108 degrees. So 3 of them, totaling 324 degrees, could meet at a vertex of a dodecahedron, but 4 is too many. Page 167. Hexagons. Each angle of a regular hexagon measures 120 degrees. 3 of them total 360 degrees, which is too much. Thus, there is no regular polyhedrons with hexagonal faces. Other regular polygons? Each angle of a regular polygon with more than 6 sides must measure more than 120 degrees. 3 of them, coming together at a point, would total more than 360 degrees. Therefore, there is no regular polyhedron with faces of any other kind. The regularity of these shapes implies that each one can be inscribed in a sphere. That is, it can be placed inside a spherical shell in such a way that all its vertices are on the sphere. Love it. This was of great significance to the Pythagoreans, who connected 4 of the polyhedra with the 4 elements of the physical world. Fire, connected to tetrahedron. Earth, hexahedron, cube. Air, octahedron. And water, icosahedron. Plato discusses the connection between the elements and the polyhedra in one of his dialogues, the Timaeus, which tells stories about the creation of the cosmos. In it, the creator is said to have used the tetrahedron, the octahedron, icosahedron, and cube as models for the fundamental particles of fire, air, water, and earth. The problem was what to do with the dodecahedron. It had to have some significance. Plato says that it served as a model for the whole universe, and so was a 5th element. The fundamental essence of the universe. This is where we get the word quintessence, which today means the best, purest, and most typical example of some quality, class of persons, or non-material thing. Quintessence. Because of Plato's interest in them, these 5 polyhedra are known as the Platonic solids, or the Platonic bodies. Can we get more solids if we relax the demands of regularity? Suppose we require that all the faces by regular polyhedrons, but not necessarily all the same kind. So, for example, the faces could be either triangles or pentagons. We'll still require that all the triangles be congruent, that all the pentagons be congruent, and that all the vertices be similar. The Greek mathematicians, Pappus, tells us that Archimedes had considered this possibility and discovered that there were exactly 13 such solids. Because of this, they are sometimes called the semi-regular polyhedra, or the Archimedean solids. Here's an example. Start with an icosahedron. It has triangular faces which come together, 5 at a time and 12 vertices. Suppose we cut off each of these peaks. This will replace each of the 12 vertices by a new face, which will be a pentagon. If we do the cutting carefully, we can rearrange the surviving part of each of the 20 triangular faces. If we do the cutting carefully, we can arrange that the surviving part of each of the 20 triangular faces is a regular hexagon. So we'll end up with a solid that is 20 hexagonal faces, 12 pentagonal ones. It is usually called the truncated icosahedron, and it actually exists in the real world. It is the pattern on the cover of a traditional soccer ball. And that is where we will end sketch 15. So we'll call this sketch 15-1.